So this is my physics lab 1, constant velocity. So our purpose is, the reason we're doing this is to study the motion of an object at a constant velocity, which means there's no net force or change of direction in the object that we're studying. And another goal is to construct and compare computational model of the object's motion to an observed model through the use of Python for the computational model and Tracker for the observed model. Our system is the car, as you'll see later, and then our surroundings is the table and everything around, like the earth and whatever. Our fundamental physics principle is Newton's second law that net force is directly related to the change in momentum or acceleration, basically, or acceleration is caused by a force applied. So a computational model was created through changing certain values from the starter code, like adding the velocity update, position update formulas into the code. The observed model was created through a video of a car motion and it being traced using Tracker. So the preview of our results is that the observed position and the observed model and the computational model were very similar initially, and then slowly the observed model started to deviate. We're thinking through for friction or something like that, causing that negative acceleration. So physics idea is Newton's first law, so the object will stay in motion unless there's in that constant motion unless something is putting force in the opposite direction or another force is being acted on it. Newton's second law is saying that net force is proportional to the change in momentum as seen in the formula of the picture. And then constant velocity showing the same speed and direction. Velocity update formula, Vf equals Vi plus F net over m times delta t. As we can see later, the masses cancel out. And then position update, so Rf equals Ri, initial position, plus average velocity times delta t. So this is the video of my car. And basically I just rolled it and it was rolling across the table, and that's the video I used to measure. Oops. And this is the Tracker data. So as we see, I can see that the Tracker, I traced it, the car movement pixel by pixel, and because it was a frame rate of 30 FPS, the second time intervals or time steps was 0.033 seconds, and we can see that in our computational model as the initial time, or the delta t, is 0.0335. The ball's mass, we can just leave it as 1 as it's canceled out, and the velocity is negative 2.685, and I got that from doing I took the first 5 time steps and found the average velocity between that to get the initial velocity as the initial condition. And then I also updated the F net, the force net, to become 0 because it's a constant velocity, so there's no net force. And then I updated the ball velocity to the velocity update formula, ball velocity plus F net over ball mass times delta t, and then same thing with the position formula with the formulas we talked about earlier. And that's basically all I did to change the code, and I got the computational graph basically. And the red is the computational position modeling, and then the blue is the observed position. As we can see in the graph, the position is very, very, very similar, and it starts to deviate as time goes on, and this is probably due to friction on the table with the car and everything like that, and those can be other things. But basically, the overall line thing is that the observed model and the computational model are very close and very similar for the majority of the time. However, there are some errors, as we said, the deviation, so the friction on the surface of the observed model. No net force exists in the computational model, but it does in the observed model. The table could have also been slant, which could have caused an acceleration or something, but that wouldn't really make sense because it was showing a deceleration in the graph, right, because it's going up. And then model errors, so variation in tracing position and Tracker, so I could have misplaced the tracing every frame. And there's also a human error, I could have pushed the ball slightly to the slant instead of straight. And then lastly, what if and what does it mean? So what if I flip the axis? If I flip the axis, so right now our graph is decreasing. If I flip the axis, the physics would be the same, except the graph would be increasing, right? And next, what does it mean? So how many pushes and pulls to cancel force out? So the net force can be found by canceling out the forces, or finding the magnitudes of all the forces and directions, and then canceling out which cancel out, right? So the net force for the vertical, it was 0 as the table balanced out the gravitational force and stopped the car from going all the way to the floor or flying away. Friction was a horizontal force in the observed model. Slightly, it was minimal, but it wasn't 0. And that's also something that we can see that wasn't canceled out in the observed model. So this is my physics lab 1. Thank you very much.